So let's continue where we left off. And we were talking about the chemistry of organolithium reagents, what you could do with them, what they were useful for. And to summarise, they are strong bases, very, very strong bases. T-butyl lithium is the strongest base that you commonly use in chemistry. So T-butyl lithium is a stronger base than N-butyl lithium. Why is that? Why should T-butyl lithium be a better base than N-butyl lithium? Anybody like to offer a... What are we talking about when we say this? So N-butyl lithium is CH2, 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 CH3, and T-butyl lithium is... So why is this a stronger base than that one? The negatively charged group is more stable. Actually, I would argue that if it's more reactive, a stronger base, it's sort of the same thing as saying that it's less stable. It's actually, I'm not so much interested in stability. What dictates how strong a base something is how much negative charge is on the carbon atom. How negatively charged is the carbon atom? Now, clearly, in both cases, we have carb anions, but what you should appreciate, largely from your organic chemistry, is concepts like positive inductive effects. So a methyl group exerts a positive inductive effect, and what we've got here are three methyl groups pumping electron density into the carbon, which is formerly negatively charged. So we are going to have a more electron-rich carbon atom in T-butyl lithium, rendering it a stronger base than N-butyl lithium. But let's be very clear about this. They are both very strong bases. This just happens to be an even better base than the other one. Now, if you go down Group 1, then you should recall from your first year chemistry that the electropositivity, or put another, the electropositivity is going to increase, put another way, the electronegativity decreases as you go down Group 1. And what that's going to mean is that those bonds, which we've already described in the case of the carbon-lithium bond as being very, very polar, they get more polar still, to the point where methyl sodium is similar to methyl lithium, but it is even more polar. By the time you get to methyl potassium, that is not really a molecule at all. It is an ionic solid consisting of discrete potassium cations and discrete methide anions. And so its carb anionic behavior, which relates to how reactive it is even greater. So potassium methyl potassium is an extraordinarily difficult solid to handle. It has an ionic lattice, but let's not be confused about it. If you take that ionic lattice, it's not like sodium chloride. If you add sodium chloride, it dissolves in water, and you hydrate the sodium cations and the chloride anions. If you were to take methyl potassium and add water, then you would get exactly the reactivity that you saw with methyl lithium. You would get the protons in the water reacting with the methide anions to give you methane, and you would make potassium hydroxide. But essentially what you're finding is you're getting ever more ionic properties as you go down the group, and that's to be expected because those are less electronegative elements. So there's a summary. I'm not proposing to go over this again. It was only a couple of hours ago. Hopefully these summary slides are useful when it comes to revision, because those are the take-home messages so far today, and those are the sort of things that you should know when you're coming to revising. Now, if we move from lithium to beryllium in our periodic table, then we will appreciate that we've gone from Group 1 to Group 2, so we're now talking about divalent elements. They have two electrons, and they're going to use those two electrons to form two bonds with two methyl radical species. How do we make those kind of compounds? Well, we can start off with beryllium dichloride, and here is our first example, and by no means our last example, of a metathesis route to an organometallic reagent. So you have to be able to make organolithiums, but once you've made organolithiums, you can use metathesis chemistry, these salt exchange reactions, to make any number of new organometallic molecules. So this is a general reaction. Often, and I've said this last year to you, students say to me, do I have to memorise every single chemical equation you've put on your slides? Well, clearly the answer I'm trying to drum home as early in this course as possible is no. If you recognise how to make an organolithium and you know that organolithiums react with electrophilic metal halides, then this is a general class of reaction. And you only need to remember that you can use metathesis with organolithiums and metal halides to make any number of new organometallics. So here we have dimethyl beryllium. Now, how much will you encounter during your chemistry careers dimethyl beryllium? Well, the answer to that one is essentially you won't. Beryllium is extremely toxic. It's also very low abundance. So there's not much beryllium out there to play with, and it's a very good job because beryllium compounds invariably are extremely toxic and very bad to know. So there aren't a lot of people doing beryllium chemistry. So one doesn't tend to dwell very much on organometallic or organoberyllium chemistry. If you have dialkyl beryllium compounds, then they adopt this sort of a structure. They adopt a structure with tetrahedral beryllium centers and bridging alkyl groups. Now immediately you will recognize that those bridging alkyl groups are exactly the same chemically speaking, they have the same bonding type chemically speaking to the bridging hydrides that you saw in compounds like borane. So here what we have is a 2-electron 3-center, 1, 2, 3-center bond. So this is another example of 2-electron 3-center bonding. Remember in lithium it was 2-electron 4-center bonding that we saw. And if you have 4 bonds to each beryllium with bridging alkyl groups, that is a recipe for a polymer. So this chain continues indefinitely. And what that means, because this is a polymeric material, is you'd expect this material to be have very low volatility and to actually be really quite poorly soluble. Remember we had discrete aggregates for organolithiums, which had non-polar and therefore really very soluble. These linear polymers are going to be very poorly soluble and have very low volatility. What's the electron count for beryllium? So you have 2 alkyl groups on beryllium. Beryllium is in group 2. Okay, so you have 2 electrons from beryllium, 2 electrons, 1 from each of the alkyl groups, 4. So these are also electron deficient compounds. So if you did take these and react them with a good Lewis base, you would expect that Lewis base to break up the polymeric structure and to form a Lewis acid Lewis base adduct with these compounds. And so that's beryllium. We won't encounter much in terms of beryllium, but I spent a little bit of time talking about it because I spend a little bit less time talking about organomagnesiums, which are structurally speaking exactly the same. So how might we make one of these organomagnesiums? Well, you can make organomagnesium reagents through a metathesis route using lithium alkyls. You probably know there are other ways to make organomagnesium reagents, but it's perfectly reasonable to say that you would take magnesium dichloride and react it with 2 equivalents of alkyl lithium to make magnesium or dimethyl magnesium. That would work. That would work, but there are more convenient methods. This one is called transmetallation, and in transmetallation you start off with a rather peculiar reagent, a dialkyl mercury. Now, this is not something that I would encourage you to do, largely because of the toxicity of dialkyl mercury compounds. We'll come to mercury in its own right in a few minutes. Dialkyl mercury compounds are really not nice to know. I deal with all sorts of things, but dialkyl mercury compounds make me a little bit nervous. If you take a dialkyl mercury compound and react it with magnesium metal, you get a transmetallation, a change of the metal here, and what you produce are magnesium alkyls and mercury metal. And these dialkyl magnesium compounds are just like the dialkyl beryllium compounds. They are linear polymers. And although it's drawn like this, I haven't done anything to indicate this is clearly, because we know how many electrons associated with an alkyl group, this is 2-electron 3-center bonding. So if you want to consider what's actually going on, then once again you can consider a sp3 hybridized methyl group. That shouldn't be too difficult for you to consider, which has an orbital containing a pair of electrons. So if you like, it's a methide anion. That orbital containing a pair of electrons will overlap, interact with 2 vacant sp3 orbitals on our magnesium center, those 3 orbitals will go together, the 2 electrons, 3 centre bonding. And this, of course, is exactly, as I've said a couple of times already, exactly the same bonding mode, exactly the same electron-deficient bonding mode that you talked about with Professor Botman in diborane. Right, something a little bit more familiar already to you, apparently. Direct synthesis, and particularly the direct synthesis of organomagnesium reagents. And the one you've all come across, the Grignard reagent. So what is going on in that case? Well, if you start off with magnesium metal, that will react with an alkyl halide. So that is our direct synthesis. This is another example of a so-called direct synthesis. That reaction is normally done in diethyl ether. It needs to be done in rigorously dry diethyl ether, but unlike the lithium chemistry, it's perfectly okay to work under nitrogen. So you can use nitrogen as your protective atmosphere here. The drier your diethyl ether, the better this will work. And what you produce is a Grignard reagent, which normally I guess you call RMgX as a generalization, where R is your alkyl group, magnesium, and a halide. Now, what I would have added here that perhaps you haven't seen before is if you do this in diethyl ether, then you will actually have a solvated species which has diethyl ether ligands present. What number would you expect N to be? So in a Grignard reagent, you dissolve it in diethyl ether. What number of diethyl ether molecules would you expect to find coordinated to your magnesium centre? So the structure of Grignard reagents is not that. Let's take a bromide, for example. Someone said bromide earlier on. That is not the structure in solution of a Grignard reagent. Organometallic chemists should have a problem with that, or inorganic chemists should have a problem with that, because if we do a quick electron count on this beast, how many electrons are there around magnesium? There are 4, because we have a sigma bond here and a sigma bond here. An alkyl radical and a bromo radical are going to be 1 electron donors. Magnesium is in group 2, so you have 2 electrons from the magnesium. That is a 4 electron species, so it is electron deficient. So I'll ask you again, and I guess the key point is, how many electrons does a diethyl ether molecule donate? How many diethyl ether molecules do we need to satisfy the requirement for an electron octet? 2. So the species that we'd expect to find here is not that, and in fact I don't want to draw something that looks square planar either. Clearly what we're going to have in this system is 2 diethyl ether molecules coordinated to this. So the structure that you'd expect to find would be this. And indeed, if you're very careful about the way that you crystallise these species, you can actually crystallise out from diethyl ether solution Grignard reagents as 4 coordinate compounds and get the crystal structure and prove to your satisfaction that that is the case. And of course here we have an octet of electrons. Now, Grignard chemistry is very interesting because I've already said that it isn't simply RMgX that is present in solution. The predominant RMgX species is going to be a solvated one, but the chemistry of Grignard reagents is richer still. They participate in an equilibrium, and that's the equilibrium that we have on the screen here. 2 equivalents of a Grignard reagent, which we've abbreviated like this, but we know the species is going to be solvated, are in equilibrium with a dialkyl magnesium and a magnesium dihalide. And that is the Schlenk equilibrium. Now, the Schlenk equilibrium was used to properly describe, or first used to describe the chemistry occurring with Grignard reagents. But it's also true that many other organometallic species, which have the structure of 1 alkyl group, metal, and a halide, not just magnesium, participate in equilibria like this. And these all collectively get described as Schlenk equilibria. But the Schlenk equilibrium is the one that refers to the chemistry of Grignard reagents. Now, does this matter to the average organic chemist? No, it doesn't, because what we have here is an equilibrium reaction, and this RMgX species, how does an organic chemist use a Grignard reagent as a rule? Yeah, they use it to form carbon-carbon bonds, and what sort of functionality are they exploiting? So, you know, organic chemists love to talk about electrophiles and nucleophiles. So which is our Grignard reagent? It's the nucleophile, or very specifically, it's the carb anionic part of it that is our nucleophile. And that will attack electrophilic carbon atoms in molecules such as carbonyl groups. So the classic reaction in organic chemistry of a Grignard reagent is it reacting with a ketone type species to form a new carbon-carbon bond. Of course, dialkyl magnesium also got a carb anionic alkyl group. So this would react in exactly the same way. Do I know which of these species is largely responsible for the chemistry of Grignard reagents? I believe it is this that is largely responsible for the chemistry of Grignard reagents. But if you started off with dialkyl magnesium because for some reason you absolutely didn't want to have any halide present, then you would get essentially the same kind of reactivity of your organic reagent. Right, so this is the Schlenk equilibrium. Let's suppose that we want to use this equilibrium to isolate not the Grignard reagent. That's what you get predominantly when you do the direct synthesis method. You want to use direct synthesis, but you want to make the dialkyl magnesium reagent. You know it's present in this equilibrium. How do you use that fact to isolate it pure? Well, what you can do is manipulate the equilibrium. And what Schlenk did and others is they add 1,4-dioxane. Now 1,4-dioxane looks quite a bit like a diethyl ether molecule, or maybe two diethyl ether molecules. And the beauty of 1,4-dioxane is it is what I would call a divergent, meaning pointing in different directions, base. So you have two basic sites in a dioxane molecule, one here and one here, but they can't possibly coordinate to the same metal. You're all used to bidentate ligands. Dr. Claydon spent a long time talking to you about bidentate ligands. This is a ligand that has two donor sites, but it couldn't possibly donate both of those sites to the same metal. So what does it do? It donates them to different metals. And since we know that we want to add two equivalents of a Lewis base to our magnesium species to get to an electron count of 8, you have two sites of functionality on your magnesium, you have two sites of functionality on your Lewis base. That is a recipe for a polymer. And what happens when you add dioxane to magnesium halide is you get a polymer. As I've just said a little bit earlier, polymers are insoluble. The polymer will precipitate from solution, and as it precipitates from solution, by Le Chatelet's principle, it's removing this species from the right-hand side of the equation, and so the equation shifts to the right-hand side. And if you can precipitate all of the magnesium halide, you can take your Grignard all the way from a Grignard to a dialkyl magnesium reagent. So this can be used to get halide-free dialkyl magnesium. Okay, now that's group 2 chemistry that we talked about. Let's move swiftly on to look at group 12. That seems to be skipping a few things. Then perhaps it is, and we will come back to this transition metal chemistry. Remember, group 12 is in the transition metal block. But it's also true that group 12 contains the elements zinc, cadmium and mercury. Why do we not consider the elements zinc, cadmium and mercury to be classical transition metal elements? Exactly, because they don't have a partially filled d orbital. So they don't do redox chemistry. The chemistry of zinc, cadmium and mercury is the chemistry of the metals in their oxidation state 2, where they have a d10 configuration, and so it's not partially filled. So the chemistry of group 12 is similar to the chemistry of group 2, with one very, very important exception, and that's the one stated right at the beginning of this slide. These zinc compounds that we'll be talking about here do not participate in 2 electron 3-center bonds. Now, there might be many of you who wish there was no such thing as electron deficient bonding modes and 2 electron 3-center bonds. If you go to zinc chemistry, you can have all the wonder of organometallic chemistry without this new concept of electron deficient bonding modes. So, If you're not having electron deficient bonding in these species, then if you have a dialkyl zinc reagent, remember dialkyl magnesium is a linear polymer with 2 electron 3 center bridging alkyl groups. Zinc doesn't form bridging alkyl groups, so if you have a dialkyl zinc reagent, it's a linear molecule. Not a polymer, but just a linear molecule with the structure R, zinc, R. So these have a very simple molecular structure. They're not polymers. How do we make them? Well, hopefully, even at this early stage, you'll be recognizing a general route to organometallic reagents, metathesis chemistry. Zinc is definitely, I think you'll agree with me, to the right of lithium in the periodic table, so we can use organolithium reagents and zinc halides to make these species. So zinc dichloride, 2 equivalents of an organolithium reagent or a Grignard reagent. So we have Grignard reagents in our toolbox now. Grignard reagents are to the left of zinc in the periodic table. Magnesium is a more electropositive element than zinc, so we can also use Grignard reagents to do this metathesis chemistry and make a dialkyl zinc compound and 2 equivalents of our metal halide, or 1 equivalent if we are using magnesium in these systems. You can also do the chemistry through transmetallation, although, as I say, I wouldn't recommend this route. In particular, dimethylmercury is the most toxic compound I've ever heard of, actually. People are only really recognizing now just how dangerous dimethylmercury is. Not mercury metal, I'm not talking about the stuff that leaks out of your thermometers in the teaching laboratory. That's not very good for you, but in the small quantities in fume hoods, it's not going to do you any harm, okay? I'm talking about dimethylmercury. Dimethylmercury is a very volatile source of mercury metal that can get into the body, pass through barriers into the brain very easily, get hydrolyzed to produce methylmercury species and go after the cysteine residues and other sulfur-containing amino acids in the brain and do a lot of harm very quickly. So dimethylmercury is very dangerous, but you can, if you so wish, use it to make dialkyl zinc reagents. Dialkyl zinc reagents are very good alkylating agents if you require a really quite mild alkylating agent. So in organometallic chemistry, if we have a metal that might be reduced very easily, then we would typically use a dialkyl zinc as our alkylating agent. If you have a very reactive organic molecule which might have all sorts of different functional groups and you want to target one specific functional group, i.e. the carbonyl function in these species, and not react with several others or have complicating chemistry, you might choose to use a dialkyl zinc reagent. Under zinc is cadmium. Cadmium, of course, is very toxic in itself. You can make cadmium alkyl compounds through, surprise, surprise, metathesis chemistry. So we can make dialkyl cadmium compounds in exactly the same fashion. The cadmium carbon bond, so zinc is an electropositive element, not as electropositive as magnesium, but it is. And so you have a delta positive charge on zinc, delta negative on carbon. As you go down group 12 from zinc to cadmium to mercury, then you find the electropositivity of these elements decreases as you go down group 12. What that means is that the bonds are becoming progressively less polar. So the zinc carbon bond is still quite polar, have significant carbanionic properties. The carbon cadmium bond is much less polar, and that makes it a very selective reagent indeed. So normally we're associated with Grignard reagents. They go for the carbon in a carbonyl function. An organocadmium reagent doesn't actually react with carbonyl functions. And so if you have, for example, this species here, an acid chloride. If you have an acid chloride and you were to treat that with a Grignard reagent, then what you would expect is for one equivalent of the Grignard reagent to substitute the chloride and one equivalent of the Grignard reagent to attack the carbon of the carbonyl, and you get 2 new carbon-carbon bonds being formed. If you don't want that, then you can use a cadmium reagent. The cadmium reagent doesn't react with carbonyl functions. It only reacts with the carbon-chlorine function, and we can have a selective organic synthesis reaction to make a new ketone in these systems. Okay. So this is a different kind of selectivity associated with a less polar carbon-cadmium bond. Okay, if you went to mercury, then clearly you would say, well, this is the trend that we're getting. By the time you get to mercury, the carbon-mercury bond is barely polar at all. The electronegativity of carbon and mercury are very similar. So this bond is not very polar at all. And so what happens with mercury chemistry is quite different from most of the organometallic chemistry that you and I are going to be concerned with. We're going to get back in a moment to really electropositive elements. Mercury is not a really electropositive element, so these reactions are specific to mercury and don't have much bearing on the rest of our organometallic chemistry. But you can do direct synthesis. So this is a reaction we've seen before. If you start off with an alkyl halide and mercury metal, this tends to require some promotion, so irradiating it with light is a good way of getting the reaction to go. You can make alkyl mercury halide compounds. Alkyl mercury halide compounds, perfectly accessible. You can also take mercury halides, which exist of course, mercury dichloride, react that with an organolithium reagent, seen that before. You can do that once to make a organomercury chloride. You can do it twice to make a dialkyl mercury compound. Now this is the really strange reaction that you won't see generally for organometallic chemistry, so please don't walk away with a suggestion that most organometallic reagents will do this, or most metals will do this. If you start off with benzene and react that with mercury acetate, we get a reaction called mercuration. And in mercuration, we form a carbon-mercury bond and we liberate acetic acid. Now, if you saw most organometallic reagents with acetic acid, you would expect the chemistry to go in the opposite direction. So if ever you saw an equation saying how would phenyl lithium, for example, react with acetic acid, ethanoic acid, then you would say, well, the lithium carbon bond is delta plus, delta minus. The acetic acid obviously has a delta positive hydrogen atom. So you would expect it to go together to make benzene and lithium ethanoate, or acetate, as it would typically be called. So this is very unusual organometallic chemistry and comes about because of the very low electronegativity, the electronegativity of mercury being very similar to the electronegativity of carbon. Now, mentioned a couple of times, I guess the message is probably going home, that dimethylmercury makes Dr. Lancaster nervous. Dimethylmercury definitely makes me very, very nervous. I've made a point this year in 2C32 of encouraging you all to wear proper gloves where it's appropriate to do so. I have to tell you that if we were, and of course we're not, working with dimethylmercury, even those gloves wouldn't help you. You have to have metal-lined rubber gloves, so a thin layer of metal, to protect you if you're going to be working with dimethylmercury, because that small volatile molecule is capable of passing through thick marigold-type rubber gloves, almost as though they're not there. And it's an extremely dangerous compound to know. It actually has, or believed to have, the same sort of toxicity as other mercury compounds. Most mercury compounds are toxic, but find it somewhat more difficult to get into the body very quickly, or tend to be present at low concentrations. The volatility of dimethylmercury and its ability to get into the body quickly is what makes it particularly toxic. But there are actually enzymes in the body which are capable of taking normal mercury salts and making organometallic reagents out of them, making methyl mercury compounds. So there are many bacteria living in the oceans that take the effluents from our chemical plants, they turn them into methyl mercury cations. These cations are then ingested by, say, crustaceans. Crustaceans are eaten by fish. The fish are eaten by people, and the people get poisoned. So there was a very, very famous incident in Japan. Anyone ever heard of it? The Minamata Bay, where there was a chemical plant pumping mercury-containing effluent out into the bay. The fishermen were fishing it, and lots of people died, and many more were seriously brain damaged by mercury poisoning. So it's an accumulative brain poison that goes up the food chain and causes more damage the more you're exposed to. That wraps up group 12 for the time being. Let's move on and look at the chemistry of group 13. So group 13 obviously starts with boron. So you've recently learned quite a bit about boron chemistry, I hope. How do we make organometallic boron reagents? Well, surprise, surprise, we can do metathesis chemistry. So if we start off with a boron halide, react that with a Grignard reagent, we can make a trialkyl boron reagent. These are trigonal planar molecules. They're trigonal planar molecules. They do not form dimers. Okay. Now, contrast that with the boron hydrides that Professor Botman was talking about. The boron hydrides that Professor Botman talked to you about do form dimeric compounds. They have bridging hydrogens. If you have a compound that is a dialkyl boron hydride, that will also be dimeric, and it will form it through dimerizing through bridged hydrogens. But if you have trialkyl boron compounds, just to be awkward, because we've seen that alkyl groups can bridge, trialkyl boron compounds are trigonal planar monomers. But of course they've got a vacant orbital, and wherever you have a vacant orbital, you have a Lewis acid. So trialkyl boron compounds function as Lewis acids. And if your Lewis base happens to be another equivalent of an alkyl anion, or a phenyl anion in this case, you can actually make tetraaryl tetraalkyl borate anions. So this is a Lewis acid, Lewis base adduct between triphenyl boron and the phenyl anion from a phenyl lithium molecule. And these compounds are, as you probably recognise, described as 8 compounds. So if you have a negatively charged compound, it is a 8 ATE compound. So this is tetraphenyl borate. Anyone come across tetraphenyl borate? Do you use tetraphenyl borate in gravimetric analysis in year 1? Still do that? Tetraphenyl borate is a weakly coordinating anion, and is used wherever you want to basically have a fairly reactive cation. You don't want the anion to interact with it, then you use things like tetraphenyl borate and its derivatives. Okay, so that was pyrophoric, and hopefully slightly entertaining in the process. What we need to recognise there is that essentially the best illustration of what is meant by pyrophoric were the attempts to put those fires out. So you never saw this spontaneously bursting into light, apart from when there was that small leak at the end from a tube. So essentially, if something is pyrophoric, it bursts into flames immediately being exposed to air. It does not need a source of ignition. It is its own source of ignition. So although the fire was put out by the dry powder and put out by being smothered by vermiculite, as soon as it was exposed to air again, it bursts into flames once more. And that is something that's pyrophoric. So he said at the beginning of that clip, essentially, if you have a alkyl aluminium or neat alkyl lithium, the thing about trialkyl aluminiums is they are in fact liquids. So you can have a neat liquid of trialkyl aluminium, or indeed dialkyl zincs are also liquids. They're volatile pyrophoric liquids, and that is a nasty combination to have. So frequently, you can't really extinguish these things very easily. You saw how much dry powder was needed for these. You saw how much vermiculite, a sackful for a relatively small field there. The best thing to do with these things is to let them burn themselves out, if at all possible, because typically you wouldn't be working with tens and tens of litres of these things. You'd only have a small amount present. We will get to why these species are pyrophoric and so reactive in a few moments. So that is the chemistry of organoboron. Now, Professor Botman has spent quite some time drawing analogies between boron-nitrogen bonds. Some of these have been picked up on the Topic 1 practical report, so I've read all about them. Drawing analogies between the chemistry of boron-nitrogen. Of course, a boron-nitrogen fragment is isoelectronic to a carbon-carbon fragment. But it is a polar fragment, whereas a carbon-carbon fragment wouldn't be polar. A boron-nitrogen fragment is polar. So we can have Lewis acid, Lewis base adducts between these species, and this is isoelectronic, this molecule, to a hexamethyl ethane molecule, but it is a polar species. And of course, Professor Botman would have talked about these organometallic derivatives, the so-called borazines or inorganic benzene compounds, where you have an alternating combination of nitrogen boron, double bonds and single bonds. These, of course, although they are isoelectronic, or that molecule is isoelectronic to hexamethylbenzene, Professor Botman would have stressed that it isn't the same, it's not fully delocalized. These are much more a series of localized bonds, and because it's polar, this is a much more reactive, much less stable molecule than benzene itself. How do we make organoaluminium compounds? Well, hopefully many of you would have said to me, well, you take aluminium trichloride and 3 equivalents of a Grignard reagent or 3 equivalents of alkyl lithium. By now, I know you've only had 1 3/4 lectures or so, but by now I'm hoping that this is exactly the kind of thought process you have. Aluminium is to the right of lithium in the periodic table, so if I want to make an organoaluminium compound, I can use lithium chemistry to do it. Now, organolithium reagents are very expensive, so although you'd be absolutely right, and that would be a perfectly reasonable way to do it on a small scale in a laboratory, if you need to make these reagents on a very large scale, then it's not a very economically viable route to do it. So can you do direct synthesis? Well, you can do direct synthesis of aluminium alkyls, but the problem with that is it doesn't go all the way through to trialkyl aluminiums. It stops about almost literally halfway there. So if I mix aluminium metal and methyl chloride, then what I get here is the aluminium methyl sesquichloride compound. So we have a dimeric compound which has 3 methyl groups and 3 chloride ligands. Now, what structure would this species here have? You will have talked with Professor Botman, I think, about the structure of aluminium trichloride. What's the structure of aluminium trichloride? It's dimeric. And how does it dimerize? Okay, so far on this course we've seen bridging methyl groups and we've seen bridging chloride groups. So which will it be? I don't think this should be a particularly difficult one. Basically, here are our extreme possibilities on this slide. So the bonding in trimethylaluminium is exactly the same concept that we've already seen as the bonding in, for example, dimethyl magnesium. But of course, in trimethylaluminium, you don't have to form an infinite polymer in order to satisfy the requirement to involve all the orbitals. In trimethylaluminium, all that you need to do is to form a pair of electron deficient bonds for every aluminium species rather than 4. And so in the case of trimethylaluminium, what we get is a dimeric structure like this. In the case of aluminium trichloride, this is the structure of aluminium trichloride. And so my question to you is, we've now encountered a molecule that is somewhere in between. What structure will it have? Okay, there's a big clue on this slide. This molecule is described as having an electron octet and being an electron precise compound. This molecule has an electron sectet in both cases and is clearly not an electron precise compound. So I'll ask you one last time, what structure will trimethylaluminium twice or trimethyl dialuminium trichloride have? Yes, it will be a chloride-bridge species, because if you've got a choice between an alkyl bridge compound and a chloride bridge compound, the chloride bridge will win every time, because only the chloride bridge actually introduces more electrons into our count. So a bridging chloride is always preferred over a bridging alkyl group. Bridging alkyls implies electron deficient bonding. In a bridging chloride, all you're making is a dative bond, and we're all very familiar with the favourable nature of dative bonds. So that's the structure here. I don't want to talk us through here. I don't expect us all to remember this, but industrially speaking, in order to get through all the way to trimethylaluminium, you actually have to add sodium. You add sodium into this, sodium will generate essentially a methyl sodium species in here, and that will get you through to your trimethylaluminium compound. There are other routes into organoaluminium compounds. So this is required if you want to make trimethylaluminium. Trimethylaluminium is really important in the polymer industry. Trimethylaluminium is used to make a reagent called methylaluminoxane, which is essentially a partial hydrolysis product of this. That's really important in generating things like your polythene bags that you're all so keen to use when you come out of the supermarket. That requires trimethylaluminium in that chemistry. Triethylaluminium in these systems, triethylaluminium is made through a different route. So triethylaluminium can be made through what's known as Ziegler's synthesis, taking aluminium metal, hydrogen gas and triethylaluminium, scrambling this all up to make a dialkyl aluminium hydride, and these species actually insert ethylene. So this will insert ethylene or ethene to give us triethylaluminium. This chemistry means that trimethylaluminium is very, very expensive. This chemistry means that triethylaluminium is a lot cheaper. So triethylaluminium is preferred whenever you don't have to have trimethylaluminium because it has a much more convenient synthesis. There is no CH2 compound that we can react with an aluminium hydride in order to make a methyl group. The smallest alkene you can have is clearly ethene. So this is the shortest chain. The ethyl chain is the shortest chain you can use or make using this synthesis. Now, why do we need buckets and buckets and buckets, and don't have it in an empty bucket, by the way, of trialkyl aluminium? Anyone know? Trialkyl aluminiums are actually used in the synthesis of things like detergents. So we've seen how reactive. Most of those demonstrations on that film were trialkyl aluminium, and specifically triethyl aluminium. So it's a very, very dodgy compound to know. What happens industrially is people take triethyl aluminium and then essentially add ethylene to it or ethene to it. You get longer chains. So you get aluminium with long chains, maybe C12, C14 chains on the aluminium. So we have a long chain aluminium alkyl. You then bubble oxygen through it. We've seen how reactive these things are. You bubble oxygen through it. The oxygen inserts into the aluminium carbon bonds to make alkoxides. These alkoxides are then hydrolyzed with water. So you insert oxygen first and then you hydrolyze. And that gives you, well, what would it give you? You have an aluminium alkoxide species and you react it with water. What will your products be? Well, your products are going to be aluminium hydroxide and alcohol. So you have a long chain alcohol. Is this getting any clearer? What are long chain alcohols good for? Exactly. So on large scale, there's a massive requirement for making detergent molecules. And in order to make detergent molecules, you need long chain alcohols. And you can make these long chain alcohol molecules by inserting oxygen into aluminium carbon bonds, hydrolyzing it, and liberating the alcohol.